In this video, we're going to sum up what we've learned about atomic theory and how we got to the current atomic theory. So in order to do that, we're going to use a grid that has 5 columns, here they are, and here are the titles, and we're going to fill in 5 rows on this grid to summarize the history of atomic theory. So you might be asking, why are we interested in the history of atomic theory? Aren't we just really interested in what it's like now? And one of the answers to that question is that the history of the atomic theory is that scientists started out with a very simple idea of what an atom was and ended up with a much more complicated idea. And isn't that the way we learn? We learn the very basics of something first, and then we add to that knowledge as we go along. So that's what we're going to do in this case. So we're going to start in the early 1800s. Remember, thousands of years ago, the Greeks had an idea that atoms existed, but in the early 1800s, it's really John Dalton who gets the credit for using experiments to come to the conclusion that atoms exist. He did some chemical reactions, and he knew about other chemical reactions that other scientists had done, and found that the elements combined in certain proportions, and that led him to think that these elements must be made of tiny units, and those were called atoms. Now, Dalton didn't think much about, or didn't really have any basis for thinking that atoms had working parts inside them. He just thought of them as tiny little solid spheres, very much like miniature billiard balls, and that's why his model is sometimes called the billiard ball models. Atoms, in his mind, were just tiny little solid spheres. Almost 100 years later, along comes a fellow named J.J. Thompson, who does a very famous experiment called the cathode ray tube experiment. And we're not going to worry too much about exact or specific dates. We just want to know the order that things occurred in. So Dalton in the early 1800s, J.J. Thompson in the very late 1800s, Thompson's cathode ray experiment in which he put an electrical current through a very thin, a very dilute or very unconcentrated sample of gas, and he was able to observe a stream of something, and that stream he was able to bend in one direction or another using a magnet. So he concluded that the stream had some sort of a charge to it, and this charge had to have come from someplace. So that led him to conclude that somewhere in these atoms there were some negatively charged parts. Now, his idea was that the atom was a sphere, just like Dalton thought, a sphere of, in Thompson's mind, positive charge with little bits of negative charge in it, just like the pieces of fruit in a pudding, and that's why this model is sometimes called the plum pudding model. So a few years later, around 1910 or so, Ernest Rutherford does his very famous experiment. His experiment is the gold foil experiment. He directed a stream of alpha particles at a very thin piece of gold foil, and found that many of those particles went straight through the gold foil. A few of them curved slightly, and even fewer still, but a countable number, bounced straight back. And so that led Rutherford, sorry, we're talking about Rutherford now, that led Ernest Rutherford to think of the atom as something that had mostly empty space, and most of its mass was in a very small but dense nucleus at the center of the atom. And this was the first idea of the fact that there is a nucleus in the center of atoms. And so Rutherford's model of the atom is called the nuclear atom. Rutherford's colleague at the University of Manchester in England was Niels Bohr, and shortly after Rutherford came up with the idea of the nucleus, Bohr did some calculations in order to try to explain why elements, or some elements, had certain properties. and he attributed those properties to what the electrons are doing. So Bohr's idea was that electrons are not all the same. They're not just floating around randomly, but they're moving around the nucleus of an atom in very specific paths. And they can change from one path to another, and when they do, they either have to gain more energy, or they have to give up some energy in the form of light, and that's why we observe things like the color of a metal changing as it gets heated to very high temperatures. So Bohr thought the electrons were going around the atom like planets around the sun. This model is sometimes called the planetary model. It's often called the Bohr model, after the Niels Bohr who created it. Now, this model is pretty easy to understand. The nucleus is like a little sun. Remember, this is all very, very tiny. We can't see it. We're just building a model to help us understand, building a mental model. So the nucleus is like a sun. The electrons are like planets. There's electrons in different orbits, just like the planets around the sun are in different orbits. And that helped explain a lot of the things that we saw, or that were observable about certain elements. But even Bohr came to the conclusion very quickly that this explanation wasn't good enough. And that led to a whole bunch of other information, which was gathered from the work of Einstein, a fellow named de Broglie, Heisenberg. Yes, Heisenberg's a real guy. Schrodinger's also a real guy. Chadwick, many other people during the 1920s and 30s, after Bohr came up with his model, did calculations and various experiments, and they came to the conclusion, after a lot of back and forth on this now, they came to the conclusion that electrons don't behave just like tiny little particles, but they have a lot of the characteristics of waves of energy. So electrons are sort of part particle, part energy. And that led to the idea that we really we cannot say for sure where an electron is in an atom at any point in time. We can only calculate where they probably will be at any given point in time. So we can calculate probabilities. Now, if this is hard to understand, you're not alone. This is a very complicated subject. Since we don't know for sure where an electron is at any time, we can't draw the electron as a little point around the atom, but so scientists draw a sort of a cloud of space around an atom where the electrons are most likely to be. And the math that they use to come up with the shape of that cloud and the probability of where an electron is called quantum mechanics. So this model of the atom, the most recent model of the atom, is sometimes called the electron cloud model for the way it depicts or demonstrates the electrons, or it's called the quantum mechanical model after the very, very complicated math that's used to create it. And towards the end of this period of time, in the 1930s, this fellow Chadwick demonstrated that not only are there positively charged protons and negatively charged electrons in atoms, but there are also some particles in the nucleus that don't have any charge, the neutrons. Now, since the 1930s, scientists have definitely added some information and some complexity to the model of the atom. They found that the neutrons and protons and electrons have smaller parts themselves, but this is where we're going to stop. In fact, we'll use the Bohr model most often. It's easy to understand, but we do want to know that the Bohr model is a useful model, but it's not as good. It doesn't do as good a job as describing what's going on in the atom. So there you have it. There's a brief summary of some of the history, some of the high points, the highlights in the history of atomic theory. What are atoms like? Here we see the progression that scientists made in figuring out what's going on inside of these tiny submicroscopic little atoms. Thanks for listening.